In this video, we're going to be taking a look at how to predict reactions and also wrap up the different types of reactions that we've been encountering in chemistry so far, how to look at reactions and determine which of these different reaction types a reaction should belong to, as well as how to predict what the products for some reactions should be. This can be a rather challenging topic, but the emphasis on reactions is, I think, a really good thing to carry forward with you in chemistry. And as you get into further topics, always bringing things back to the reaction is some advice that I always give to my students, and something that I think if you embrace, you'll get a really great result. All right, let's take a look at some reactions in the following video. All right, to start things off, let's keep in mind that we've studied quite a few different types of reactions, and I'm just going to kind of go down the list and break down the different ones that we will be looking at. The top two here, synthesis, decomposition. Here we have either two things coming together or one thing breaking apart. Combustion is a pretty specific type of reaction where we have organic matter, so something containing carbon, hydrogen, maybe oxygen, burning in the presence of oxygen to create carbon dioxide and H2O. This is a pretty wide class of reactions, even though it may seem pretty specific. And whether this organic matter is gasoline or propane or wood, combustion is characterized by the combination with elemental oxygen forming carbon dioxide and water. Double displacement we've looked at quite a bit, and especially so in our net ionic reaction video, where we have two soluble ionic compounds that come together to form a precipitate. And keep in mind that we do need the formation of this precipitate to actually be a double displacement reaction. If instead we have all aqueous products, then in reality, no reaction may have occurred. Single displacement looks similar to double displacement, but here we just have a single product, like the copper solid here, which is actually a reactant, that's substituting into the silver nitrate reactant. This is basically kicking out the silver as a cation to create solid silver, and the copper is going to be our product. Second to last, we have an acid-base neutralization, which features a hydroxide containing compound and a compound that has H plus in place of where we might expect a cation to be. These two will combine together and form water, and we'll be left with a salt product, NaCl as well in this case. But remember that salt can refer to just a general ionic compound, not necessarily just table salt. Key to the acid-base neutralization, though, is forming water out of the basic OH minus and the acidic H plus, which is not exactly a cation, but is taking the place of one here. And finally, we have a redox reaction, which is characterized by electron movement. And here, we're going to talk about this a bit more. We're going to learn how to track the oxidation numbers of the different atoms within the different species here, and that's going to help us determine whether it's a redox reaction. And keep in mind that many reactions can be classified under multiple ones of these. For example, the single displacement and combustion reactions are both also redox reactions, and this acid-base neutralization does look a whole lot like a double displacement reaction as well. So while we might be able to call it that, other different names for reactions may not always apply. To start things off with precipitation reactions, which we've looked at already, think about net ionic reactions. Remember that precipitate is a formation of a solid. So when things come together and we form a precipitate, that is a solid formation. And often this is from a double displacement reaction. The reaction shown here on the side, where we have the formation of this lead-2 iodide, is the following, where we have two aqueous solutions coming together, so potassium iodide and lead-2 nitrate, and we're forming the lead iodide. And note that we can show this with the net ionic as shown here, keeping in mind that the potassium ion and the nitrate ion are both going to be in solution, whether in the reactant side or the product side. So the net ionic reaction is just going to be the lead-2 finding the two iodides to form lead-2 iodide, which is shown here as the yellow precipitate that comes out in solution. Okay, so with this in mind, let's think about the different reactions we have looked at so far and think about what are the products for these double displacement reactions. And a good way to think about this is, well, what are the net ionic reactions? Because that can really help, once we've predicted the products, determine whether a reaction even occurs or not. So I recommend you pause the video here and go ahead and see if you can predict the following products. All right, hopefully you've been able to give this one a try. Let's go ahead and look at our solutions. So in our first reaction here, our products are going to be as follows. We really just want to switch the two cations and see what forms once we do so. So while we have the lead paired with the nitrate, now let's see if lead paired with carbonate might make a reaction. Same thing with the potassium. Potassium's initially with carbonate, now with nitrate. And be absolutely sure that when you're predicting your products, that you're also making sure that your compounds have equivalent contribution of positive and negative charge. Note that even though there are two nitrates in the initial reactant, we only have one in the product that we're proposing, and that's because the lead has a 2+ charge in the initial nitrate, and potassium has a +1 charge in the final nitrate. Therefore, we're going to need to balance this afterwards, but we absolutely need to make sure that our predicted products are balanced themselves. We want to check their states, and for this we want to use our solubility table, remembering NCAA number 1, which can help us get most of the way there with predicting soluble products. We'll find that lead carbonate is not on NCAA number 1, but potassium nitrate is. We know right away potassium nitrate is aqueous, and the lead 2 carbonate, we can look at our solubility table and determine that that also is not going to be soluble. We want to balance our equation, and we end up with the following balanced chemical equation. Net ionic is going to look like as follows. Note that we have a lead 2 in combination with a carbonate that's going to form lead 2 carbonate. And this is our balanced net ionic reaction here, where we have lead 2 with 1 carbonate, and that's going to make a lead 2 carbonate product. In our second example, we have the sodium hydroxide and this copper 2 acetate that are again going to try to switch, and we're going to form copper 2 hydroxide and sodium acetate. Take a look at our solubilities again, and we notice that the acetate is aqueous and the copper hydroxide is actually going to be insoluble, which again, we really do want to verify with our solubility table. Again, having sodium, acetate, chlorate, ammonium, or a group 1 metal tells us it's going to be soluble, but it doesn't necessarily say if it's not on that list, it's definitely insoluble. Balance our equation, and we end up with the net ionic here, which shows that all that's happening is copper is finding the 2 hydroxides to form copper 2 hydroxide. Final one, we again want to switch our ions around, but this time what we notice is that they're all going to be aqueous. This barium chloride isn't on our NCAA number 1, but when we consult our solubility table, we actually find that it is soluble as well, and therefore when we do our net ionic, we end up with no reaction here. All 4 of these ions are going to be aqueous both before and after, and therefore there's not going to be a precipitate, and while this may look like a double displacement reaction, it is actually a no reaction reaction. Okay, so that's double displacement reactions. The other thing we want to look at in this video is oxidation reduction reactions or redox reactions. And for this, oxidation numbers are incredibly helpful. Now, the most important rule, I would say, is the 4th one here, and that really is a reminder that oxidation numbers are a way of keeping track of electrons. When we add up all the oxidation numbers within a compound, we absolutely need to get the number that is the charge on the molecular ion, and most often for a molecule, that number is going to be 0. If a number isn't shown, then that number is 0, right? But if we have something like a polyatomic, then it may have a charge there as well. The following rules are great general rules, but again, not as important as the fact that all of the numbers absolutely must add up to the total number of electrons on that compound that's in excess or whatever. That is the most important rule. We need to keep track of our electrons. These happen to be great rules for getting us started, where halogens are generally -1, oxygen's generally -2, and hydrogen's generally -1. And these rules will get you most of the way. However, if they break down because we're not able to adhere to these rules while also getting the sum to equal the charge on the molecular ion, then there are some hierarchies with which they'll have to be flexible. Finally, if we have cases where we pretty much just have one thing that's there, if it's a monatomic ion, so for example Cu+, then the oxidation number is +1. It actually has a charge, the oxidation number is equal to the charge. Charge is a very solid physical property, whereas oxidation number is a way to keep track of electrons. But if it's just one thing and it's got that charge, oxidation number is the same. And a lot of the oxidation number direction that we're going to follow should reflect what we know about charge as well. In an elemental substance, meaning the element that has a charge of 0, then it's going to have an oxidation number of 0 as well. So good rules to remember, but I think if you really embrace rule 4 here, those ones seem like pretty much the only answer that it could be. Okay, so why don't we assign some oxidation numbers here? What are the oxidation numbers for all the atoms in the following reactions? And let's classify these reactions. Go ahead and pause the video here, give this one a try, and see if you can get the right answers. All right, hopefully you've been able to give this one a try. If we take a look at our top reaction, we have the following. So we have carbon -4 to pair with hydrogen, which is +1. We get a -4 for the carbon because the hydrogens like to be +1 in a compound, and there are 4 of them. Altogether, they have to equal 0, which is the charge on the CH4 methane reactant, and therefore carbon is going to be -4. Oxygen, our second reactant, is 0. It's elemental form all by itself. CO2, we have -2 for oxygen. That's what oxygen likes to be in a compound. Carbon now we figure out based on the fact it's all got to equal 0 because that's the charge on CO2 and therefore must be +4. And water, we have -2 for oxygen. That's what it generally likes to be. +1 for hydrogen, that's what it generally likes to be, and that actually does make them just turn out to 0 anyway, and so everything works out pretty well with our oxidation numbers. This is a redox reaction and a combustion reaction. Note that carbon is losing electrons. It's going from -4 oxidation state, which suggests it has 4 more electrons than it should, so to speak, and in its final state, it's in the +4 state, which shows that it has 4 fewer electrons. Note that it doesn't actually have those electrons, but we use these oxidation numbers to keep track of whether or not it's gaining or losing, and in this case, it is losing electrons. Oxygen is going from 0 to -2, and therefore is going to be gaining electrons. We have oxygen that's being reduced, carbon that's being oxidized, and we have a redox reaction. Taking a look at the second one here, we get the following oxidation numbers: sodium +1, oxygen -2, hydrogen +1. The bromine in the second reactant is -1 as well, still a halogen, and everything here should look relatively familiar. It does follow the rules pretty well for this second example. And note here that this one is not a redox reaction because while we take all of these oxidation numbers, note that none of them change. Sodium, bromine, oxygen, hydrogen all have the same oxidation numbers on the reactant and the product side, and therefore there's no movement of electrons from one species to another, and this one is not a redox reaction. It is, however, an acid-base reaction. We have hydrogen and hydroxide forming neutral water, and we could also think of it as a double displacement, though not a precipitation reaction because we don't have a solid product being formed. All right, let's look at a few more reactions and let's try to predict what type of reaction each of the following are. So go ahead and pause the video again and see if you can predict what types of reactions these all should be. All right, let's go ahead and take a look. The top reaction is a decomposition. We have one chemical substance that's breaking apart into multiple. And note that while it does take 4 of the phosphorus tribromide to break apart, it's still a decomposition reaction. We only have one thing that's becoming multiple different things, therefore decomposition. Our second reaction, we have another combustion reaction. We have burning in oxygen, making CO2 and H2O. This should be distinctively combustion, hopefully by now. And note that combustion reactions are also going to be redox reactions. If you track the oxidation numbers, you'll see that they do change. And I think a really good sign that you're going to have a redox reaction is if you have something in its elemental state on one side that is not in its elemental state on the other. Keep in mind that in the elemental state, oxidation numbers are going to be 0, and it's not very common that we have a element or atom within a compound that is going to have a oxidation state of 0. Finally, we have copper 2 hydroxide, phosphoric acid, making water. and copper to phosphate. And this one is going to be a double displacement reaction. We have ion switching. It's also an acid-base reaction because we have the hydroxide and the H plus on the phosphoric acid that are coming together. And so that will be how we would classify this reaction. All right, I hope you enjoyed this walkthrough of different reaction types, predicting reactions, and really focusing on what is the reaction really will take you very far in chemistry, as it is a step that can seem tempting to gloss over or not feel too sure of. So definitely one that's worth practicing and one that'll definitely pay off in the long run.